Okay, so we're going to talk real quickly here about geometric probabilities. And so let's create a couple of circles here. Okay, we're gonna create a couple of circles to talk about these. Okay, so let me draw on the circles here. I'll call this circle A, and this will be circle B. And if these were drawings of a set inside of a space, I could ask you, what is the probability of A? And you would say, well, it's the number of elements in A over the number of elements in the space, right? But these don't have spaces. I mean, they don't have elements in these places here. The circle doesn't have any elements in them. Yes, there's a center, but that's not what this means. So when we're talking about geometric probabilities, we stop using the number of elements, and instead we just call what is the area of A, right? That kind of makes sense. Over the area of the space. So let's say that maybe this is a game you're playing with a bullseye and a target or something. You're either throwing a dart, or maybe you're dropping a water balloon from up above, and you're guaranteed that it's going to land like somewhere inside this. So maybe you're dropping it inside of an enclosed cylinder or something. You know that this is going to land somewhere here, but what's the probability that it lands inside of here? So you just find the area, and let's say the area of this circle here was 2, and let's say the area of the big circle is 15. Then you would say that your probability of hitting the circle A would be, in your game, would be 2 over 15, because those were the respective areas, right? 2 over 15. Now I'm going to confuse things a little bit, because I'm going to add in circle C. So what if I said, okay, you win if you get, maybe this is drop a penny into a fountain, right? And right here on the fountain is a bucket, or into this well is a bucket, and into here is another bucket, and you win a prize if you get your penny to fall into either of these buckets. So then what would be the probability of getting it into, let's say, A or C? Okay, what is the probability you got it into either one? Well, as you can guess, we would do that by taking the area of A and adding the area of C, right? And then we would divide that, of course, by the area of B. So now we'll give CO an area of 1, so we could say that's 2 plus 1 over 15, or 3 over 15. Okay, so our probabilities are improving because we've said either one of these landing spots represent a winner. So they represent part of this probability. So see, all we're really doing is we're taking the probability of one space and we're adding the probability of the other space geometrically. That's all we do. And really that's all you're doing with any probabilities that you figure out, whether you're using geometric probabilities or just sample spaces. You're just adding together the probabilities of both. Now this is what happens when we have a union, right? A union, right, which is given like this. It says, what is the probability of A union C? And you might remember, as opposed to an intersection, which is just where they overlap, but a union is where we add together. We take whatever we have in A and whatever we have in C, we add them together and we divide them by this space, right, B. In this case it's areas, but in a regular set theory, we could just have them be elements, the number of elements here and the number of elements there. The intersection, of course, right, that was written, we'll kind of cover this. We have covered this already quite a bit, intersections, right, because we called them conditional probabilities, okay, intersections. And we talked about intersections quite a bit, but basically it would be written as the probability of A intersection with B. Okay? And then we're just looking at the overlap, right? Wherever they overlap, that would be an intersection problem, okay? Is looking for the overlap. And we could do a geometric problem that involves an overlap. We would just draw our circles such that they overlap. And in fact, that's what I'm going to do now. Let's say that we had circle D. Here we have circle D. Oops, D. That's circle D. And what if we said, what is the probability of getting it in? Now we're going to make C go away. And we said, what would be the probability of getting the intersection? An intersection would just be this area in here, right? Where they overlap. But what if I said the probability of the union of A and D? Right? Well, we take the area of gotta be careful I don't get going too fast, of A plus the area of D, right? The area of A and I should just call it A and D. I take those areas and I add them together. And I divide them by the area of B, right? But there's a problem. Because if I include this area when I calculate the area of A, then I've already counted for it. And then when I calculate the area of D, okay, then I will have double counted it, right? So when I add together any areas for union problems, I need to take the area, or the number of elements in this set and the number of elements in that set, but I have to subtract the overlap. So I'm going to subtract the intersection of A and D. I have to do that. Otherwise, I run the risk that I'm double counting a certain area. So this is true for any kind of probability problem. This is called the addition rule right here. Let me get a good color here. This can be a contrasting color here. We see. And this is called the addition rule. Did I spell that right? I'm working on the addition rule. We're going to take all the probability of one and all the probability of another. I do it with talking about geometric probabilities here so we can actually see it. I think it helps if you see it. We take one, right, the probability of A, we take the probability of D, but we subtract the probability of the overlap or the intersection, right? So that is really important to do. So I'm going to pause this now. We're going to go back and do some Khan Academy problems. Okay, so now we have some Khan Academy problems. This one's called Adding Probabilities. And what we're going to do is we're going to calculate the probability. See, now it says here, what is the probability of A or B? So the probability of Mark's little brother, I haven't even read this problem, but it has to do with getting dressed or something. That Mark's little brother selects an outfit with a white shirt and gray slacks. So let's make a little note here. Maybe I'll draw right here. So white and gray equals A. So A is a white shirt, right, and gray slacks. So that's A. So let's find A here. White shirt, gray slacks. That's this one here. And I don't see any other ones here, right? White shirt and gray slacks out of this outfit. Or an outfit with a black shirt. Okay, or an outfit with a black shirt. So let me write that out. Different color. So a black shirt. Oops, that's supposed to be an S. A black shirt equals B. Okay? So black shirt, well, that's either of these two. Okay? So quite simply, we calculate what A is. Right now, is there any overlap here? Well, I kind of overlapped when I drew it, but the reality is this is one outfit of 6. So this would be 1 over 6. And these are 2 over 6. So the probability that he picks one either A or B. You add those together and you get 3 over 6, which is 1 over 2. So that's what we're going to put in there, 1 over 2. Okay? And that's how that work is done. Now hopefully we'll be a little bit more complicated. Oh good, this will be good. Okay, so you have 20 customers eating dinner at a local restaurant. The restaurant accepts cash or credit as forms of payment. Of the 20 customers, 4 have enough cash to pay their meal, 16 have a credit card, and 3 have enough cash and a credit card. So let's draw this, okay? Let's draw it out. Here's our space, right? Inside of our space exists 20 total people. So 4 have cash. So that's not a very big group, but we'll call them as 4, right? And then we have a big group, which is 16 that have there are 16 that have a credit card to pay. Okay? And then it says of the it says of the 24 have enough cash, 16 have a credit card, and 3 have enough cash and a credit card. So the 3 in here could do either because they have cash and they have the credit card, which tells me that I have one outside, one that has only cash, and I have 13 that have only credit cards. So how do I find that? If I know there's 16 total in this green area and 3 are also in the blue, then that means 13 are only in the green, and I have 4 total in the blue and 3 of them are in the green as well, so 1 is exclusively in the blue. So now we can answer these questions. So the probability that the customer has enough cash. Well, cash is 4 over 20. Right? Which reduces to 1 over 5. Okay? Probability the customer has a credit card, 16. Oh, they're not asking us if it works, by the way. Just having a credit card doesn't mean much if it's not going to work for you. Okay, so 16 out of 20, which reduces to 4 out of 5. Okay? The probability the customer has enough cash and a credit card. So the and, remember we talked about like being in the intersection, right? That they have cash and, that would be these 3. So it's 3 out of 20. Oops. Oh gosh. 3 out of 20, right? And then the probability the customer has enough cash or a credit card. Well, that would be, let's do our probabilities here. That would be all the cash. That was 4 out of 20 plus enough credit card was 16 out of 20, right? So one or the other, that ends up being 20 out of 20. Was that right? What about this overlap? Didn't we double count the overlap? We have a little bit of a problem. 3 of these people that had cash or credit were double counted. They were counted as 3 of the 4 here and 3 of the 16 there. So guess what? We've got to take away the 3 in the overlap of the 20. And we got to take away that. So our answer is going to be 17 over 20. Now I don't know what happened to the other three. Right? There's got to be 3 more people that exist. Here, here, and here are 3 people. They don't have cash or a credit card, right? Let's try filling in and make sure that Khan Academy agrees with these answers. So the number that had enough cash, that was 4 out of 20, which we said was 1 over 5. The probability that they had a credit card, that was 16 out of 20, that was 4 out of 5. Probability to have enough cash and a credit card, that was the overlap, that was 3 out of 20. Right? 3 of them had enough cash and a credit card, and so the probability that they had enough cash or a credit card, we'd say, was 17 out of 20. And I hope that they have it right. Yes, we do. I don't know what happened to those other 3. I feel bad for the, I own my own restaurant, so I feel bad for the restaurant owner, because apparently he has 3 customers that cannot pay for their meal. Okay? That's how we do the addition rule. That's how you figure it out. And I'm going to let you go ahead and work on these problems.